Hello, this is Dr. Juma coming to you with uh, chemistry of class 2 carbonyl compounds. But this time around, we want to look at um, alpha beta unsaturated aldehydes and ketone. Previously, we have looked at ketones without any unsaturation around it. You remember ketones and aldehyde. You remember if from that carbonyl, this position here is referred to as alpha, that position is referred to as beta, away from the carbonyl carbon. Okay, so in the previous lectures, we have dealt with such kind of compounds, whether straight chained or even cyclic. Okay, we do not have any saturation in the alpha and beta positions. Okay, so the chemistry, the compounds that you're going to look at today is, you'll notice, is a bit different. Okay, other aspects have to come into play. And so when you talk about alpha beta, for example, look at the compound that we have here. Uh, the carbonyl carbon is there as indicated, and away from the carbonyl carbon, the alpha position, the beta position, between those two positions, there is an alkene group. And so we say that it is alpha beta unsaturated. Okay, alpha beta unsaturated. So we want to show you how the chemistries of this molecule differ with the chemistry of the other compounds or carbonyls that you already know. Now, as shown here, remember that oxygen, being electronegative, uh, as shown by this arrow here, will tend to pull electrons toward itself and therefore leave the carbonyl carbon slightly positive. And when you draw resonances, then we can have a full positive charge on the carbonyl carbon. So it shows that that carbon, which is directly attached to the oxygen, is electrophilic. Okay, so it is vulnerable to attack by nucleophiles. Okay, that one you already know. Now, the new thing about this kind of compounds, if you look at the other resonance bit of it, okay, is that the carbonyl carbon being electron deficient, okay, and noting that the pi bond is electron rich, it's possible for the pi electrons to be drawn towards the carbon so that we have a double bond there, okay. And of course, that then means that the carbon at the alpha position also becomes electrophilic. It is electrophilic. So that would also mean, therefore, that that position is prone to an attack by a nucleophile. Okay, so then look at what's new here. Let me erase all that we have there. What's new here is that we have now two electrophilic positions in an alpha beta unsaturated either aldehyde or ketone. So it means the nucleophile has two possibilities, either to attack at the um, beta position or at the carbon of the carbonyl. Okay, so there are those two positions. So now there are definitions for those kind of reactions, which I want to share with you now. When an attack goes to the carbonyl of the carbon of the carbonyl, then we call that a direct attack. Okay, So it means that so far, okay, in our previous, what you've been exposed to previously, all those reactions have been what we call direct attack. Okay, we call it a direct addition, or also called 1-2 addition, because the positions, okay, where the reactions take place is place 1-2, 1-2 positions. Okay, they are next to one another. Now, when the attack takes place at the beta carbon, we call that one conjugate addition, or 1-4 addition. Okay, again, you will see that if you count the distance, okay, or the number of positions between which those two additions, okay, the incoming groups are added, they are placed 1-4 in 1-4 positions. Okay, so it is 1-4 addition. So now that's the difference, but let's build up on this one a little bit more. Okay, and let us look more closely to this direct addition, though you already know it, but now in the light of the fact that we have uh, an alpha beta unsaturation. So when a nucleophile comes, as shown here, it attacks in a direct addition the carbonyl carbon, the pi bonds of the carbonyl break, and when they break, okay, these the pi bonds there break, as shown by the arrow. We end up having a single bond there. Okay, then we have a new bond between the carbon of the carbonyl and the nucleophile. Okay, of course, what happens after that in this addition reaction is is the neutralization, the quenching of the O negative, okay, by a proton, so that we have a neutral O there. Please remember to always include the signs to show the flow of electrons. Okay, so then this is a direct addition. It's a direct addition. Then let us now look at a conjugate addition. Okay, in a conjugate addition, the attack by the nucleophile goes to the beta position. Okay, as you can see, the beta position, and this is the beta position. Of course, when that attack takes place there, then the pi bond here must break. Okay, the pi bond there, the double bond, one of the bonds, the pi bond breaks there. And what happens? We have, of course, a new bond here. It's a new bond between the nucleophile and the carbon at the alpha. Of course, then we have electrons moving at the alpha position. But then because oxygen is uh, electronegative, it will be pulling those electrons at the alpha position towards itself. Then we have the a charged oxygen as shown here. And what follows is the oxygen. Okay, this oxygen here. By the way, if you note here, as I've indicated, there are two possible resonance structures for that intermediate. This is an intermediate, but okay, it has to be stabilized by, let me show you this one using arrows. So this particular oxygen here, okay, picks up a proton so that we have a neutral oxygen. So that is called a conjugate addition, or 1-4 addition. Notice that this particular structure here can exist in two forms. What you're seeing here is an enol form. Enol. What is enol? Enol comes from the word in and all. Okay. You notice that there's an alkene here, and there is an OH here, which is always alcohol. So enol, but simply written as enol, to remove, to ensure that we don't have two vowels following one another. So it's enol. Okay. Now, so that is the enol form, but there is a keto form of the same compound. In the keto form, what has simply happened is that we have a hydrogen moving, okay, being picked up at the alpha position, and then the double bond is of the carbonyl is restored as seen here. That's a keto form, and if you look at that compound structure, is a ketone. So we talk about eno keto. Okay. Now we will talk in future lectures, maybe in higher levels, more about that. But for now, we will leave you with that. Okay. So that is conjugate addition. Now, whether direct or conjugate, okay, it depends on certain factors. Either direct or conjugate addition on an alpha, beta, unsaturated aldehyde depends on three factors. One, which we're going to be discussing, is the nature of the nucleophile. Two, structure of the carbonyl. And I know you people already have a lot that you can say about that point number two, because we have discussed it previously. Okay. And then number three is conditions under which the reactions take place. Okay. So we'll look at each of them, or probably a combination of them, as we continue with this short lecture here. Now, let's talk about the nature of the nucleophiles. Generally, nucleophiles that are weak nucleophile, okay, will always attack at the beta position. But which are the weak nucleophiles? Nucleophiles that are considered weak, some are listed here, okay. The halides, the cyanides, the thiols, the alcohols, and the amines. And generally, you'll find that there are nucleophiles that involve heteroatoms. Those are generally weak nucleophiles that are weak bases. Okay. Um, and I think you probably also already understand what the difference between bases and nucleophiles are. Bases pick hydrogens, and the nucleophiles attack, okay, at electrophilic positions. But of course, now, if you look at them, they may look the same, okay? But nucleophiles can also be considered as bases. So nucleophiles that are weak bases, as listed here, are going to attack at the beta position. So what you're going to get from them are conjugate addition products. Okay, a few examples that we can give you here. HBr, okay, you guys must now know that when you give you HBr, you can pull out the nucleophile as Br negative, okay? That is the nucleophile. This is a weak base, and so it's going to attack at the beta position. Look at this, alpha, beta to this compound. So the attack is going to go there, and that's why we see this product here, okay? Another example is an amine. This one here is a secondary amine, okay? Again, if you look at alpha, beta position, this is a beta position. So you notice that nitrogen goes to the beta. The nitrogen attacks at the beta position. So we have that product there. So two more examples I'll show you. Look at this. It doesn't matter shape. It doesn't matter whether cyclic. You put your eyes on that's why we also learn functional groups. You put up your eye on the functional group. Uh, of course, for this one here, it's like similar to how alcohols will react. Okay. Please remember that the lone pairs on sulfur in this compound here is a source of electrons. So here is the alpha beta position, and you can see that the attack, the product is a conjugate addition product. Cyanide, same thing. The position of attack will be that one there. So the product can clearly be determined as shown there. So that one is the nature of the nucleophile. Okay. Now, probably just building up on that a little more. The other nucleophile that would be considered a strong basis, and we mentioned this, are hydrides and carbanions. Carbanions. Okay, you know what carbanions are. We mentioned, we try to define, tell you a little bit more what carbanions are. Any carbon is negatively charged. Carbons that are connected to metals, those are always carbanions. Okay. These are considered to be very strong bases, and for this reason, when we have reactions with this, the attack tends to go direct. It's going to be a direct addition. Okay, please look at this. This direct addition. What is the nucleophile here? We mentioned earlier, I think, the nucleophile here is a hydride. The source of hydrides are sodium borohydride. Okay, so the hydride will go direct addition. So we have an alcohol there. Okay, so that's direct addition. Okay, again, please look at this. This is a carbanion. Okay, this one here is a carbanion. When we write CH3 MgBr, this is a carbon directly connected to a metal. Okay, and we're saying this one here is negatively charged. It's a carbanion. So it's this methyl ion here that is going to attack direct. So when they are okay, very strong bases as shown here, then you have direct attack. Okay, those are direct attacks. These are other examples. Okay, this is an interesting one that gives a combination of the nature of the reagent, okay, the nucleophile, and the nature of the substrate, which is the carbonyl compound that we're talking about here. Look at it. I want to show you something. If you look at this reaction here, we have two products. Okay, we have two products. One that involves direct addition, and another that involves indirect or conjugate addition. Okay. Now here we have a very strong base for a nucleophile, but the other thing is that the carbonyl, okay, the carbonyl carbon is a ketone. Okay, it has large groups that you see, are causing some steric hindrance, so that the access to the carbonyl becomes a bit difficult, so that even a small nucleophile is being, on a strong base, is being sent to the beta position. So there are two possibilities because of a combination of the nature of the uh, of the carbonyl compound and the nature of the nucleophile. A quick reminder, I think you should remember this. We said that the rates of reactions of carbonyl, this is the most reactive. You put an aldehyde, the reactivity decreases depending on the substituent, okay, that is on the carbonyl carbon. So you see now this one here, it's at around this area here. So the reactivity towards direct attack has been reduced, but we have a combination of products because the base is also, the nucleophile is also a very strong base. Okay. The other things, however, that can be done to ensure uh, we we direct our products, determine what products we get for our reaction as much as possible. Like for example, what we are showing here, we have changed the reaction conditions, okay, from the previous reaction. In the previous reaction, we only had this borohydride and then ethanol. But in this case here, we have included selenium chloride or trichloride. What happens is that this metal here, okay, chelates. Look at this compound. Tip, tip, tip. Okay, selenium chloride. Now, because this is a metal, it makes hydrogen to be, it activates hydrogen or in oxygen or the carbonyl towards nucleophilic attack. This activation supports direct attack, okay, or direct addition or an attack at the carbonyl, okay, because the carbonyl has been, the oxygen has been somehow protonated, not protonated, but activated, okay, when it chelates with the metal. So an attack here becomes highly likely. So with those changed reaction conditions, a direct attack is preferred. Okay, so cerium chloride activates that reaction. Okay. Now, in the case we are saying of ketone, the rate of reaction has been fairly reduced. The rate of attack to the carbonyl carbon or direct attack or direct addition is slowed significantly due to steric factors. You know, these are two big groups that are coming in. And then the reagent here that wants to attack is actually this one here. It's also a big group. An attack at the carbonyl becomes difficult due to steric factors. Okay. And so it's the conjugate addition that becomes possible. So you need to be careful when you're looking at your reaction and reaction conditions and the reagents that are involved, uh, because you see, look at those kind of factors. I mean, if you have a steric hindrance, don't force a very big group to the carbonyl. That's not going to be possible. Okay, so please note that case there then gives us a conjugate addition. Okay. Now another thing about reagents and how they uh, control the reaction. We are now comparing two types of reagents here. We are comparing Grignard reagent. Okay, that's a Grignard reagent, and a Gilman reagent. Gilman reagent is copper lithium, but if you see, it carries two alkyl groups. Okay, how is it? It looks like this. Copper lithium, because of the nature of copper, carries three. I mean 2. So this one here is a bigger nucleophile. Please note that what it is actually donating is a CH3 negative, because carbon connected to a metal is a carbanion. Okay, it's like a carbanion. And with magnesium, it's therefore is a smaller reagent that is able to access the carbonyl carbon. Okay, so if we use methyl magnesium bromide, we get a direct attack or direct addition. Okay, and when we use a slightly bigger nucleophile, okay, the reagent, okay, the way it comes, it will prefer a conjugate, a conjugate addition. Key. So you need to study this so that you're able to make right judgment when deciding on the direction of the reaction. Okay, what we have here is for you to look at home during your own practice. But I think we proceed to the next thing in the next lecture. So we will leave it there. Um, this is key for you to, you better study. It's easy for you to remember some of these things when you do practice on your own. Otherwise, we close the lecture here and we'll discard that and we stop.